Now we're going to look at solution stoichiometry with ions, but a quantitative look at this. So a little bit of a mega problem right here with a lot of components you should know about. All right, so we're going to go back to our copper nitrate plus sodium hydroxide, which we showed in the qualitative part of this video. The equation copper nitrate plus sodium hydroxide forms copper hydroxide. That's where your precipitate comes in, and then the NaNO3. All right, so now I'm asked all these different questions trying to quantify amounts of precipitate and amounts of ions left over. How do I go about doing that? So what I'm going to do is I'm going to figure out the moles of my reactant here. So I look at this, see I'm scrolling too far, is I have milliliters and molarity of copper. So I can convert that to liters times molarity gives me moles of the copper, actually copper nitrate. So I'm going to put that in moles right here. And then I'll do the same thing. The liters times the molarity gives me the moles of sodium hydroxide. The next thing I'm going to determine is an excess limiting reactant. And I have more moles of sodium hydroxide, so that's going to be an excess. Not necessarily. I'm supposed to have twice as much NaOH. 0.084 is not twice as much of this. So NaOH is a limiting reactant. The other way to do that is I could take the 0.084 divided by 2. I'd get a number smaller than this number divided by its coefficient of 1. And I'd say, oh, NaOH is the limiting reactant. We're assuming all the limiting reactant reacts. So what does that leave me with? It leaves me with, let me just scroll up here a little bit. It leaves me with nothing of NaOH. And then I say, oh, if I take the NaOH, half as much copper nitrate is going to react. Okay, this number should be less than this number, and it is. I take the difference between those. That gives me moles of copper nitrate left over. I can also look at this and say, hey, 0.042 of this reacts with 0.084 of this to form 0.042 of this, 0.084 of this. So what happened is originally I had nothing of these two, but then these things combined in a 1-to-2 ratio and formed these things in a 1-to-2 ratio as well. So ultimately, at the end of the day, I have 0.0130 moles of this solution. I have nothing left of NaOH. I have 0.042 moles of this solid, and I have 0.0840 moles of this NaNO3 solution. And that's all sitting in my container. Note the use of initial change in end. It's ice. There's a box here. It makes it an ice box and a cool way to solve some complex excess limiting reactants and really a necessary way to solve equilibrium problems when they get there. So learn the ice box. It's cool. All right, we'll keep going. We're going to try to find the precipitate of COH2. Well, I know the moles here, so somehow I have to just show multiplying by that molar mass, and I multiply by the molar mass, and I get 4.10 grams. It's pretty conscious to keep my 3 sig figs on everything, because that's what we're doing here. Now, the big part is keeping track of all these ions. What's left in the solution? I know we saw the pictures the last time. This stuff sinks to the bottom, and then these are the spectators floating around, but we got a little bit of excess of this floating around. So we do have copper ions floating around from here. We got nitrate ions floating around from here. This all sunk to the bottom. These aren't going to be excess ions. They're all part of the precipitate. But you have more, you have sodium here, and then you have more nitrate. So you have one source of copper, you have nitrate here and nitrate here, 2 sources of nitrate and 1 source of sodium. All the hydroxide sitting in the precipitate, so that's not going to be something you're going to be working with. So let's look at the next piece and kind of look at our amounts from above and how this matches up and works in. So I think I'm going to keep it like this. I look at the copper at 0.013 moles of this. And what I'm going to do is notice it's in a 1-to-1 ratio. So 0.013 moles, not divided by the amount of copper nitrate or sodium hydroxide, but the combined volume in total. So I take the 110 milliliters, the 140 milliliters, I get essentially 0.25 liters. the moles of copper over the total liters gives me this molarity of the copper solution. Okay, I'm going to do the same thing. I'm going to look at the nitrate here. This one is the most complex one, but let's look at it. So I have 0.013 moles of nitrate here, but this is like a double-decker ice cream cone. For every 0.013 of copper nitrate, I have twice as many nitrates as copper. So I got to double this number and say 2 times 0.013, which gives me 0.026. And then what I need to do is add it to the amount of nitrate here, which is 0.0840. Notice it's not a subscript, so I don't have to double it here because that's already been accounted for when we did our 1-to-2 ratio here. So I'm going to take that 0.026 from here. I'm going to take the 0.084 from here, add those together. You can see that down here, and it's going to give me 0.026, 0.084, 0.110 moles divided by total liters, which is 0.250 liters again, and I get 0.440 molarity. I'm expecting it to be quite a bit bigger than the other one. There's multiple sources of it, and that's there. Okay, my last job is to figure out the Na plus. Just going back to our equation, I guess, up here, we have Na over here. Remember, this Na is all gone, but this Na is from right here. It's 0.084. We don't worry about that. That's already been accounted for. It's a coefficient. So we got 0.084 moles over my 0.25 liters, and that gives me 0.336 molarity. So this is all the ions, and that is their correct concentrations, and that is why. So just one final aside, I talk about this because this can be a little bit confusing. Why, if I have 0.013 moles of copper nitrate, is there twice as much nitrate in there? It's like ice cream. It's a double-decker ice cream treat where you have a copper cone and a nitrate scoop. And what happens if you trip and you stumble and the cone goes flying and the scoops go flying? You have twice as many scoops as cones left over. So that's why this number is twice as big as this. I could break up the single decker cone, NaNO3, just like that, but that's not as dramatic because 0.084 of this breaks into 0.084 of this and this because everything's in a 1-to-1-to-1 ratio. All right, good luck working with those, and let me know if you have questions along the way. Thank you.